In this example, we're asked to look at this simply supported beam, which is loaded with this triangular load that extends from A to C. Two things we're asked to find. One is, what are the reactions of the beam at ends A and D? And B, if we would make a cut through B, what shear force and what bending moment would we expose there in the left face of the cut at B? We're going to do this problem obviously in two parts, A and B. For the first part, the FBD that we need is one of the entire beam. So I'm going to draw the entire beam, have reaction forces at A and D, so AY and DY. There's going to be a load which is acting on the beam at some distance of capital H, which I'll define it here in just a bit, where there's a force of magnitude F which is applied. And if I call this X and Y, we're going to be eventually doing summation of forces and moments on this here. Before I do, though, let me define what I mean by F. F is equal to the total area under that triangular load. It's a triangular load, so it's 1/2 the base, which is 2L over 3, times the height, which is W naught. So that gives us a load here of W naught L over 3. Yeah. The distance H is going to be equal to 2/3 of the total width of the triangular load, which is 2L over 3. So that's going to be 4L over 9. So again, we're replacing the triangular load, but it's single force equivalent, which is equal to the area under the load with a point of location of 2/3 the distance from the left over to the right. From this, I'm going to write down an equilibrium equation where I sum my moments about point A, the left-hand side. And so from that, I get the applied force F. It's located at a distance H to the right of A. That moment is in the negative Z, so I put the negative sign there in front. dy has a moment R of L. That moment is a plus because it's in the counterclockwise sense. For equilibrium, that is 0. So from this, we get dy is equal to the resultant force F times the distance H, which I found above, divided by L. So we have all the numbers that go in here for dy. Now when I sum forces in Y, the forces I have are AY plus dy minus F. That sum is a 0. So AY, the reaction force at A, is equal to F minus dy. And so with the numbers we got for dy, this becomes F times the difference between 1 and H divided by L. So we have all the numbers it takes, therefore, to find AY. So this gives us the reactions that are required for us to find here in part A. For part B, what I'm going to do, as I suggested, was do a cut through the beam at B. So what I'm going to be showing here is a section of the beam which extends from A over to B. The forces I have on this is going to be that reaction AY that I found there in part A. We have a resultant force which I'll call lowercase f at a distance of lowercase h from the left-hand side. And because of the cut, we have the shear force V. This is the shear force acting on the left side of the beam due to the right-hand side. Same way with the bending moment there of M. That's the bending moment on the left face as a result of the right face. Please keep in mind that F here is the resultant of the triangular load that's over just that section. And over here on the right-hand side, that's a W naught divided by 3. the overall width of this section. Keep in mind it's just between A and B, so this is the distance of L divided by 3. So in this case, our resultant force F is going to be 1/2 the base, which is L over 3, times the height, which is W naught divided by 3. So that gives us a resultant force of W naught L divided by 18. The location of that, distance H, is going to be 2/3 of the total width of that load, which is L over 3. So that distance is equal to 2/9 of L. So this is again replacing the triangular load by a single force equivalent of F. So from this one, when I sum forces in Y, I have AY, I have minus the applied force F, minus the shear force V that we're trying to find. From this, I find that the shear force V is equal to AY, which I found in part A, minus F, which is given above. So we have all the numbers that go in there for V. Lastly, I'll do a moment equation. I'm going to do this about point B. Summation of moments about B gives me an AY. It has a moment arm of L over 3. It's in the negative K. The applied force F, it has a moment arm of L over 3 minus H. And then the couple there of M, which is at that face, that total for equilibrium is a 0. So therefore M is equal to AY, found above, times L over 3, minus F times L over 3 minus H. F we know. So everything goes into M, we know. So there is M. So I guess in the end, the point of this problem is that in order to find the internal force couple results here, the cut through B, what we had to do first was we had to find the reactions at A and D, in particular for what we did A. And then when we made the cut through the beam at B, we kept the left-hand side. We used that result for AY. From that free body diagram, used equilibrium to find the internal shear force V and the internal couple M that's acting on the face there at B.